Let's talk now about classifying differential equations. In other words, talking about what types of differential equations there are. There's basically three types. The first is called autonomous differential equations. Autonomous differential equations do not contain the independent variable. And that's the type of equation we've been seeing so far in this lecture. Examples are dn of t dt equals 0.49 times n of t, and dn dt equals minus 1 over 500 n plus 2, the quantity times n. Now, I can just hear you thinking, wait, I see t in those equations, and t is the independent variable. But really, the only reason we're seeing t is just because of the type of notation we're using that specifies what the independent variable is. Notice this first equation, I really could write as n prime equals 0.49n if I use streamlined notation that does not show what the independent variable is. And notice now you don't see the t. Similarly, this other equation could be written n prime equals minus 1 over 500 n plus 2 times n. And again, now we do not see the t. It's not ideal to write equations in a way that doesn't tell you what the independent variable is, but it can be done. And if you do that, you can see, yep, the independent variable is not in there. So these are autonomous. Non-autonomous differential equations contain both the dependent and independent variables. And an example of a non-autonomous differential equation is dy dt equals e to the t watt minus y plus t. So notice on the right-hand side we have both y and t. And even if I were to rewrite that derivative as y prime, I would still see both y and t in the equation. Last are pure time differential equations. Pure time differential equations do not contain the dependent variable, only its derivative. So an example of a pure time differential equation is dx dt equals 5 plus cosine of t. There's no x on the right-hand side. In fact, there's no x at all in there except as a derivative. Pure time differential equations are actually the one kind that we do know how to solve right now. So let's see an example of doing that. A stream is coming out of a dam and going into a lake. At a fixed point in time, the insect population varies according to its position along the stream, according to the equation dn dx equals 1 minus 2e to the negative x, where x represents the number of kilometers from the mouth of the stream. And I guess I should have also typed in, and n represents the size of the insect population. There's sort of a picture that goes along with that. So we've got this lake, and there's a stream going into it. And the stream is coming out of a dam. And of course, there's a reservoir behind the dam. And the stream is flowing in this direction, out of the dam and into the lake. It says that x represents the number of kilometers from the mouth of the stream. So what is meant by the mouth of the stream is the outlet where it's going into the lake. So this is the mouth of the stream. since x represents the number of kilometers from the mouth, right at the mouth we have x equals 0. And then I didn't type in that the dam is 10 kilometers from the mouth of the stream. So here we have x equals 10. Suppose the population size at the dam is n of 10 equals 20. Find the function that gives the insect population at any position x. Something to notice here, this is a pure time equation because if you look at the right-hand side of the equation, you do not see the dependent variable n. That said, this is an instance where that pure time label is maybe not totally accurate because in this instance, our independent variable is not representing time. It's actually representing a position. So time is not changing. We're taking a snapshot of this stream system at a particular time and thinking about the insect population as you look at different positions along the stream. And that can happen. Your independent variable doesn't have to be time. It often is, but sometimes things change not over time, but with respect to something else. So, how are we going to find n of x? That's what we're being asked for. Let's start with dn dx equals 1 minus 2 e to the negative x. And let's integrate both sides. Like this. We'll integrate with respect to our independent variable x. Notice that on the left-hand side, you can think of the dx's as canceling, and that gives us then just the integral of dn. The integral of dn will be n. Why is that? Well, you actually already know that if you think about it. Remember, we have a formula that says the integral of 1 dx is going to be x. It's the same thing here. Integral of just dn is n. So I have n equals, now let's see, the integral of 1 with respect to x is going to be x. So the difference here is that whatever variable you're integrating with respect to, that's the one that pops out of your integral. So if I had, I don't know, dz, say, the integral of 1 dz, let me just write that as dz. The integral of dz would be z. So that's the principle there. On the right-hand side, the integral of 1 dx is x minus the 2 comes along for the ride, and I do have to integrate e to the minus x dx. I'll use a little u substitution for that. If u is negative x, du is negative dx. So I'm going to put a negative du in for my dx. At this point, I'll have n equals x minus 2 times, I've got another minus sign, so I'm just going to use that to cancel out the minus sign in front of the 2, and I have e to the u du. So n will be x plus 2 e to the u plus a constant. So we have n equals x plus 2, and then I have to put in what u is. U is just my name for minus x, so I'll change the U to a minus x, and then I have a plus a c. So this is our function. N of x equals x plus 2 e to the minus x plus c. We're asked to do a little bit more than that, though. We're also given the information that the population size at the dam is n of 10 equals 20. So if we put that in, we have n of 10 is 10 plus 2 e to the minus 10 plus c, and that's got to come out to be 20. Solving that for c, we have c equals 20 minus 10 minus 2 e to the minus 10, which is 10 minus 2 e to the minus 10. So the particular function that we want is n of x equals x plus 2 e to the minus x plus c, but we now know that c has to be 10 minus 2 e to the minus 10. Notice the reason we were able to solve this and come up with a function is that on the right-hand side, when we integrated, on the right-hand side, we only had x's. We didn't have a mixture of two variables. We wouldn't know how to integrate with a mixture of two variables. And on the left-hand side, when you integrate, you start out with a mixture of two variables, n and x, but the x's go away.